Welcome back to How to Program. And a special warning. This show is best viewed in order, especially for this particular episode. Look guys, it took me a long time to put this episode together. I'm not gonna lie, I spent hours on this particular one. This stuff is very tricky, okay? If you didn't understand or really grasp the episodes before, please go back and watch them again. I promise you, it will be well worth the effort when you actually watch this video and actually get it. Because this video is very simple if you understand the basics, but it can be very complicated if you didn't understand something earlier. So yeah, just go back. You know, if you click on our channel, you can start from episode 1 and go on up from there. And this is actually the best way to view this channel's content. The episode we're going to cover today is episode 8, and this is binary numbers with a fraction. A fraction is when you divide two numbers together, right? So we're going to review a little bit of math first, and I already went over this part, but we're going to review it again because it's very important. So a power is a number multiplied by itself many times. For example, 10 power 2 is 10 times 10. That's 100. 10 power 4 is 10 multiplied by itself 4 times. So 10 times 10 times 10 times 10, that's 10,000. Good. Now 10 power 1 is 10, and 10 power 0 is 1. Any number power 0 is always 1. So that's very simple. The number above the base number is 10. And all of these powers here, 10 power 2, 10 power 4, 10 is the base number. So the number above the base number is called an exponent. For example, in 10 power 3, the exponent is 3. Simple. Okay, that's just a name for it. Exponent. Now, in mathematics, powers can have negative exponents. So, for example, 10 power negative 2, this would be the same as writing 1 over 10 power 2, which is equal to 1 over 100. Because we just take 10 power 2 and we just convert that to the full number. We just do the multiplication, which is 10 times 10. So that's 100. So 1 over 100, and that's 0.01 in decimal notation with the decimal point. That little point there, that's called the decimal point, right? It means fractions. 10 power negative 4, the next line here, 10 power negative 4, that's 1 over 10 power 4. That happens to be 1 over 10,000 because 10 power 4 is 10,000. And that's 0.0001. Okay, well that's pretty simple. So we can see and then we can do with 10 power 1. So 10 power negative 1. So 10 power negative 1 is 1 over 10 power 1. That's 1 over 10. That's 0.1, 0.1. Okay, so we can see generally that if you have a number y and you have an exponent negative x, that's the same as writing 1 over y exponent x. You remove the negative, right? And that goes under the 1, that divides the 1. So numbers y and x, that can be any number. That represents any number. And y and x don't have to be the same numbers. And they don't have to be 10, and they can be small, they can be big, it doesn't matter, right? Okay, so that's negative powers. If you don't get this, just stare at this a little bit. Look at the examples again. It's really not that hard, but you need to understand that a negative power is basically a 1 over the positive power, right? Negative, 10 power negative 4 is the same as 1 over 10 power positive 4, or just 10 power 4, right? Okay, so I talked a little bit about the decimal point, but the decimal point is basically, there's two ways to write a number that is not a whole number, right? That is a fraction of a number. A fraction is just a division of two whole numbers, like 1 over 4, 1 divided by 4, right? And that can also be written as a decimal number with a decimal point, like 0.25, 0.25. The point, the dot in the middle, the blue dot there, is called the decimal point. And that just tells you that on the right, it's a fraction of a whole number. So and you probably guessed this, but just as 10 has negative powers, 2 also has negative powers. And since we're dealing with binary, we're always dealing with powers of 2. So, 2 power 1 is 2, 2 power 0 is 1. We knew that. Then we get into 2 power negative 1. Well, 2 power negative 1, that's 1 over 2 power 1. 2 power 1 is 2. So 1 over 2. And 1 divided by 2 is 0.5. So 2 to the power of negative 1 is 0.5 in decimal. This is all decimal here. 2 to the power of negative 2, that's the same as 1 over 2 to the power of 2, which is 1 over 4, which is 0.25. And 2 power negative 3, you guessed it, is 1 over 2 power 3, which is the same as 1 over 8, which is 0.125, etc. It just goes on. There's a little table at the bottom here. You can see it goes, it goes into smaller and smaller and smaller numbers, and they're the negative powers of 2, and they go on to infinity. You know what I mean? They just keep going in that direction to the right. It just gets smaller and smaller. So in binary, we represent fractions with the binary point. We had the decimal point, right? Like 0.5, that's a decimal point because we're writing in decimal with 10 digits. Now, if we're writing in binary, we're going to have a binary point where, on the right-hand side of that, it's going to be fractions of a whole number. So now let's see how we can represent a fraction in binary. Let's take the decimal number 5.75 and represent it in binary. So first, we're going to represent the left side of the point. On the left side of the point, we have 5. And so 5 in binary is just 101. We've seen that before. That hasn't changed. So that's just 101. Now, the part on the right of the point is 0.75. And to represent that, we're going to need to represent it in binary. So we can break it down, just like we used to break down whole numbers for just, positive powers of 2. Now we're doing negative powers of 2. And we have the table at the bottom. So as you can see, 0.75, that turns into 1 times 0.5 plus 1 times 0.25. And we look at our table at the bottom and we see that that's 2 power negative 1 and 2 power negative 2. So our binary representation of 0.75 is 0.11 in binary. This is in binary now, right? You can see with the colors, like the blue 1 is 2 power negative 1. That blue 1, that first 1 on the right-hand side of the point represents 0.5 in decimal. And then the green 1 represents a 2 power negative 2, and that is 0.25 in decimal. So if we add all of that together in decimal, we get 0.75. Perfect. If this didn't make sense, you should just rewind it and look at it again, because this is kind of the key here. On the right-hand side, it's negative powers. You see the table at the bottom. Okay. Now, if we combine both sides that we had for 5 and 0.75, we get in binary 101, that's 5, 0.11 for the 0.75. This is called fixed point notation, because the binary point is always fixed between 2 power 0 and 2 power negative 1. Look at the table below, the little purple line here. That's the division between whole numbers on the left and fractional numbers on the right. Positive powers on the left, negative powers on the right. Yes? So that is fixed point notation. And we could write any number in binary, any fractional number we wanted to in this way with just a point, and then, and then we use whatever, whatever fractions of 2 we need to make the whole number fit, right? So we could do that. Okay, so let's talk about something else here. Certain numbers, when you write them out as binary fractions, they can fail to give you the precision you need. And we can see this happening in decimal too. So we're going to look at it in decimal first. So if you want to represent 1 over 3 in decimal, you would write 0.3333333. Okay, lots of 3s. On and on until infinity. Because the 3s never stop. It's always 3, right? However, we know that at some point we're going to run out of space. Like computers don't have endless memory. So even if we used a lot of memory, at some point we have to stop representing 3s and we can't go all the way to infinity. So there's a limit. But we do know that if we add 1 over 3 plus 1 over 3 plus 1 over 3. That makes a whole number because that's 3 over 3, and that's just 1. That's a whole 1. However, because we have to cut off and we can't represent infinite 3s, when we do 0.33333 plus 0.33333 plus 0.33333, we get 0.99999, which is not equal to 1. So we started with something we thought was representing 1/3, and we added that 3 times, and we did not get 1. That is losing precision. It is losing the representation that we really wanted. We wanted to represent 1/3, and we didn't quite represent 1/3. It was a little bit less, because when we add all 3 of them, we can see that it's a little bit less than 1. And that's because we can't store infinite numbers after the decimal point. So this same loss of precision exists in binary too, because you can't have infinite binary digits to represent your fractions. And so at some point you have to cut off. And when you cut off, you lose precision. Your number is not precisely being represented as you intended it to be. And this usually causes issues which show up when you're trying to add or subtract numbers or multiply or divide them, whenever you're trying to do an operation on them. For example, I tried this in my computer in something that is basically code. Writing code that added 0.33333 plus 0.33333 plus 0.33333, the same thing, 3 times. And I got this odd looking number that was mostly 9s with an 8 in the middle. What is this 8? There's no 8 here. However, you know, if you're doing this in decimal, there's no way you can get an 8. It's all 9s. But the only reason I got this is because of the loss of precision. We couldn't represent this number in binary precisely. You know, even a simple even something you would consider that simple, there's only, what, 7 3s after the decimal point here. And it's already losing precision. So here's the most important thing I want you to get out of this video. Even if you don't understand exactly how this works in binary or whatever, I don't really care about that. This is the most important thing that you need to get out of this video, which is do not use fractional numbers for exact calculations. For example, when dealing with money. If you try to build some piece of code that tries to calculate money amounts, like an e-commerce website where you can buy things, or some sort of accounting thing, or where you can charge people money, do not use fractional numbers. They will not give you an exact representation. You will get results like this: 0.1 plus 0.2 equals 0.3000004. This is the actual result I got in a piece of computer code that I typed this code in. It gave me that result. And that's because 0.3 cannot be precisely represented. It has to represent what's slightly off. You know what I mean? It's slightly off. It tries to represent, but it gets it wrong because it can't exactly line up the fractions with the powers of -2, the negative powers of 2, lining up with 0.3. They don't line up unless you have way more binary digits, you know what I mean, than you have, right? So there's a loss of precision. So don't use it for money. Don't ever use it for money. There's other things you can do, but mostly you're going to store the cents as a whole number, and you're going to store the dollar amount or whatever, the whole amount as a number. And then whenever you go over on the cents, you just add to the whole number, right? Okay, now we talked about fixed point. Fixed point is not the greatest thing, because it takes a lot of bits to represent very small or very large numbers. Even not that small, really. Like, for example, a number like 0.000008 in binary would require at least 17 bits to the right of the binary point to represent it. And you would still be losing precision. So really, to represent that number, you would need a lot more than 17 bits. And so computations with numbers that are written like that would just they would require a lot of space, like a lot of memory, and like even maybe thousands or millions of bits. And trying to do a multiplication or an addition of 2 numbers that are represented like that would just be super slow. It would just take a lot of computing power to do that. So we can do better. Maybe we can do a little better. So let's take a look at some solution that we can use here. So we need to go into something called scientific notation. You may have learned this in school, particularly if you took like a chemistry class or something like that. It's used a lot in chemistry. Physics also uses it. So if you took that, maybe you learned about it, but we're just going to cover it again. So taking a look at scientific notation here, you can use scientific notation to write very large or very small numbers in a compact way. And you can represent any number with or without a fraction, by the way, in scientific notation. And so we're going to look at how this works in decimal first. Let's take an example of a very small number. As you can see, there's kind of two parts to it. There's a bunch of zeros first, and then there's the actual sort of number, you know what I mean? Like there's a bunch of like digits that actually matter, which we could call significant, because the zeros don't really have any significance apart from like how many positions to the right is this number. But the numbers in orange here would be called the significant digits. And so we care about those. So we could extract them out and say that this is the same as writing 6.705 times 0.000001. It turns out that it is the same. This we could also write as a negative power of 10 for the 0.000001. And that's 10 power negative 6. So the number at the top on the first line here is the same as the number on the last line, which is 6.705 times 10 power negative 6, except the number on the last line takes a lot less space to write. So that's kind of cool. We can also write very large numbers this way. For example, 203 trillion. This is the same as writing 203 times 1 trillion, which is the same as writing 203 times 10 power 12. And you can see the 203 are really the digits we care about. The zeros are interesting, but they're not significant, other than just how many zeros are there. That's why we turn it into a power of 10. And you can see that the last line, again, takes a lot less space to write than the first line. Now, we could decide to arbitrarily cut off, quote unquote, the first number, the significant digits we've been talking about. We could cut it off anywhere we wanted. Like, for example, we could start with 203 times 10 power 12, which is what we did. Or we could say 2030 times 10 power 11. It's the same number, so that's fine. Or we could write 20.3 times 10 power 13, or 2.03 times 10 power 14. These are all the same number. They all add up to that first number there, the large 203 trillion. So which one do we pick? Well, we're going to use the last form where there's only a single digit on the left of the decimal point, because that's, that's just normalized. That's just a way we can all agree that we're going to write our scientific notation. And this is actually called normalized scientific notation. This is the correct way of writing scientific notation. We have one digit, then the decimal point, then more digits, and then we have times the power, times 10 to the power of something. So 2, 0, and 3 are called the significant digits of the number. This is what I've been saying. There's some advantages to writing in this way with scientific notation. For example, let's say we wanted to multiply a very, very large number with a very, very small number. Chemistry does this all the time. Physics sometimes too. So this is actually like a real thing. It looks very complicated at first sight. Like if we had to multiply this 203 trillion times 0.0000 whatever 461, it's very complicated. But if we use scientific notation, maybe it gets a little simpler. So if we convert the numbers to scientific notation first, normalize scientific notation, let's take a look. So this would turn it into 2.03 times 10 power 14 times 4.61 times 10 powers negative 14. Okay, well, in multiplication, the order doesn't matter. If you multiply several numbers, the order doesn't matter in which you multiply them, and it always ends up in the same result. So we can reorder this, and we can say we're going to put all the significant digits on the left and all the powers on the right. So we get 9.3583. That's 2.03 multiplied by 4.61. That's that 9.3583 multiplied by 10 power 14 times 10 power negative 14. Now, there's a trick in multiplying powers, which is if you're multiplying two powers which have the same base, the 10 is the base here. So the both powers of the same base number, when you're multiplying powers, you can just add the exponents together and you get the result. So for example, if you had a 10 power n, n being any number, times 10 power m, m being any other number, the result would be 10 powers n plus m. So you just add n and m, and then you get your result for the exponent, for the result exponent. This gives us the following result if we do this in this case. So we add 14 and minus 14, and that's just 0. So really we get a 10 power 0. 10 power 0 is just 1. And, you know, you multiply a number by 1, that's the same number. So 9.3583 is the correct answer to this very large and seemingly complicated at first, like, multiplication, which now becomes very simple when you look at it. It's like, oh yeah, 14 plus minus 14. Okay, that's very easy to calculate, you know? So that's one of the biggest advantages of scientific notation. Well, taking this principle of scientific notation, we could decide to do the same thing in binary. You know what I mean? We could do this in binary, except we would do it in base 2. So all the powers would be powers of 2. You know, and then numbers would be binary numbers. But we could do the same thing. We could say, you know, it's a plus or minus. So we would use a sign bit, you know, because we want to know if it's a positive or negative number. And we covered that before. So we just use one bit. We're not doing 2's complement or anything like that. We're just using a sign bit. And 0 for positive, 1 for negative. We'd have significant digits. Now, we can ignore this 1 dot because in binary, we know it's always going to be 1 dot. You know what I mean? Because, like, okay, in decimal it could be like 2 dot something, 3 dot something, but in binary it's either 0 or 1. And if it was 0, it wouldn't be a significant digit. So it's always 1. So that 1 is always there, no matter what you do. It's always going to be there. And so that 1 doesn't get actually stored because we know it's there. We assume it's there just by the nature of things, right? So we don't store it. We have other ways of storing a 0 or whatever, like we're just all zeros, which is fine, but, you know, so we don't store that number. We store the significant digits to the right of the binary point, and those are called the mantissa. It's kind of a cool name. I like this name. It's a mantissa or a significand with a D. There's a D at the end. That's not a typo. Those are the significant digits on the right side of the binary point in binary scientific notation. And then you would have the number y, which is the exponent, and so this would also be stored as a binary number. Now, turns out this would be a very cool way of storing, you know, fractional numbers in binary, and that is the way that we store fractional numbers in binary. It's a little more complicated than that. I omitted some of the more complicated details. You can look them up on the internet if you're really curious. But look, it boils down to this is how it's stored. There's a couple other things you might want to know, but really you don't necessarily need to know them to program. Unless you're really getting into this floating point thing, you don't need to know. There's an institute, which is called the Institute of Electrical and Electronics Engineers. ITripleE is how we call it because there's 3 E's, so we say ITripleE. They issued a document, and, you know, they issue documents because then it's standardized. If the document is issued, then everyone can do the same thing. You know, all processors can implement it the same way, like make it work the same way. And then it's very easy for processors to talk to each other, for example, or code to be written for one way because they all work the same way. So they issued a document. It's called ITripleE 754, which explains in detail how to store fractional numbers in this way, in scientific notation and binary. Very cool. So now at this point, there's a very important thing to understand here. And that is, and let me show you the previous slide here. The way the number is represented here means that the actual number, if we were to represent it in fixed binary point notation, the thing we saw earlier where the binary point does not move and just is in the same spot all the time, we would have to convert this number. And the digits in yellow, the significant digits or the mantissa, would be in a different spot. You see what I mean? Like they would actually have to move in fixed point notation to be in the correct spot because the exponent means that we are going to move it a certain number of places to the right or to the left of the binary point. So those numbers are actually like not where they're supposed to be, quote unquote, right? That means they float around. Depending on how big or small the exponent is, they're going to float around. So we call these types of numbers floating point notation or floating point numbers. This is where they get their name. So ITripleE 754, I put a little reminder at the top here in case you forgot what all these things were, but this was 2 slides ago. You could back it up on the video. But there's 2 types that are defined by ITripleE 754. One is called single precision, which is just called float. Float for floating point. So now we get what floating point is because the point moves around, potentially. Like you can change where it is in a real number that you're representing, right? So single precision called float. It uses 32 bits total. Those bits are broken down as follows. 1 bit is the sign bit. That's the first bit. The most significant bit is the sign bit. Single precision, which is called float, and this uses 32 bits total. And so this 32 bits are broken down this way. The 1 bit is a sign bit. This is usually the first bit is a sign bit. 0 for positive, 1 for negative. We saw that. 8 bits are used for the exponent. So you can represent an exponent in 8 bits. And then 23 bits are used for the mantissa. These are the significant digits that we talked about. Now, if this isn't precise enough for you, which it might not be, depending on what you're writing in terms of code, you can get a double precision. And this is just called double. Double for double precision. This uses 64 bits total. 1 bit is still a sign bit. We still only need 1 bit for the sign bit. We don't need more than 1 bit. 11 bits are used for the exponent, so you get a little bit more room on the exponent side. And then 52 bits, which is all the remaining bits, get used for the mantissa. This is the significant digits. Okay, well, that's pretty simple. Now, a little bit more stuff about this IEEE 754 here, floating point numbers. These are very fast in modern processors, particularly processors made for graphics, because as it turns out, when you're trying to represent things in a 3D game, for example, like a video game, you know, like it looks like a real world in 3D, you know, 3 dimensions, you're always representing every point in space, like on a wall or on a cube that they're representing in 3D, or like whatever environment they're representing. There's lots of little points. All those points, their coordinates, like where they are in space, are represented with floating point numbers. All of them in this way. And so all the calculations that go into figuring out how to show the 3D environment on the screen is all floating point math. So they build processors that are just very good at doing floating point math. And those are what you get out of a graphics processing unit mostly is floating point processing power. Because a general CPU is not, you know, it can do floating point, but it doesn't have like tons of floating point, you know, it's not mostly floating point, but a graphics processing unit is mostly floating point, like it mostly deals with floating point operations. A floating point number still loses precision, like we showed earlier, but it gets close enough in most cases. However, like I said, don't use it for money or exact amounts. When you need to deal with exact or precise scientific calculations or money amounts, don't use a floating point number. Every coding language usually has a float or a double. They may have other names for them, but you know, this, like real, sometimes you get the word real. That's just because it's in mathematics, a real number is a number that can be a fraction. Like, anyway, it's a little more than that, but sometimes they use that word, so you'll see that. And then in some languages, even though it's called a float, the language is actually giving you a double. Yeah, so sometimes you say, I want to float, and you're thinking you're getting 32 bits, but you're getting 64 bits. It's not a bad thing. You just get more precision. That's okay. It doesn't hurt anything. So you just check the documentation of whatever you're working with, and then it will tell you what you're getting for real. Well, that was floating point numbers. And the next thing we're going to see is we're going to look at a different counting system, and I promise this is the last one we'll look at before we move on to more practical things. But it is important to know this one. It's called base 16, and we'll look at that next episode. So look forward to seeing you then. And you can also like our Facebook page to get updates as soon as the episodes come out, and I really recommend you do that. And if you really like our channel, you can also like the video, comment, and subscribe, and let us know that you like it. All right, we'll see you next time.